Greetings, guys. Okay, so this is episode 8 of the ESP32 Adventures. I started this because I wanted to learn more about these ESP32 boards, with specifically the S3 version because it has capabilities of being an OTG on the go host USB port. And I found, of course, that one from Expressive that I dealt with in earlier episodes, it has everything built in, an SD card interface, two USB ports, a device and a host port, and so on and so on. So I've been able to experiment with that, and I've did a bunch of episodes on that. So as a reminder, the first 3 episodes were getting started with these boards and dealing with TFT, LED display, and getting the SD card working and so on. But in episode 4, we actually experimented with and got the USB HID device mode working, so we could actually output data through the USB device port and make it the PC think it was a keyboard. Then in episode 5, we went to experiment with the Bluetooth facilities, and we were able to emulate a HID human interface device, also keyboard. So we got those two working. Then in episode 6, we actually attached a real keyboard to an ESP32 S3 board, and we were able to get input from it. That was, of course, running it in host mode. And there was an episode 6B where we further analyzed the HID USB traffic using a logic analyzer. And in episode 7, which is the previous episode, we actually put that together and we created a USB to Bluetooth keyboard dongle. With other words, inputting data from the keyboard and outputting it exactly through the Bluetooth interface. And in this episode, we are actually going to go a little bit further with that. What I actually were talking about earlier in the earlier episodes is this is a PS2 keyboard. It actually has a socket on there for, the old-fashioned PS2 serial interface cable, which PCs used to have up to about 20 odd years ago, and before they started using USB keyboards and mice. However, I started looking at the code and writing the code in order to do that. And this is actually the code here. I created a PS2 to HID keyboard file, and I actually got as far as to write the code to get an interrupt service routine running for the input from the two wires. There's a clock and a data wire, and the clock wire you use in order to trigger an interrupt, and when the signal goes low on the falling edge of the clock signal, you would actually read from the data port and create bytes of input. So I actually got as far as to create a table here for converting the codes that the actual PS2 keyboard outputs, which is different from the USB and Bluetooth outputs, the HID codes. So this is a table where I could look up, convert the codes, and all of that was working just fine. But then when I started working on the actual routine here, get the HID code from that table and so on. So when I started coding this, as you can see, there is sort of an error there with these modifiers. I started to realize that I would start to become responsible for capturing the Control, Alt, Shift keys and so on, even the Windows key on the modern keyboards is also a modifier key. It actually acts as both. And I would have to do certain actions and so on the incoming characters and so on. That was actually starting to become very tedious. So then I started to think by myself, in the last episode 7, we were successfully hooking up a USB keyboard and outputting the codes. There was nothing to do. So then I started to realize that I have this device that I used to use on this keyboard. This is it here. It actually has a USB plug on it, as you can see. So it's got USB outputs, and it has two inputs, one for a mouse and one for a keyboard. We're not going to use the mouse input, of course, at this stage. We're only interested in the keyboard input, so the keyboard could be plugged in, and it actually does all that work for us. It does the conversion from the PS2 codes to the actual HID codes that we need, and the USB output, of course, is completely compatible with our little chow board that we are using, ESP32 S3 board. It has little pads on the bottom where you can actually solder the wires for the D plus and the D minus of the USB port. So then I opened this thing up and I found there's a little board in there with a little, it's got a chip underneath, a blob of epoxy or something like that in there. And I also realized I wouldn't be needing this thing anymore. I would never use it, so I might as well actually use it. And actually, we could reuse the code that I did in episode 7 and make that work and put that inside of the keyboard. So then that gave me the components in order to complete this project. All I had to do was wire it in and write some, test out the code. I did add a little bit of code to it just for testing, which you will see when we get to the code. I have the code in actual fact on my GitHub site. Which is there. And this is actually the Chow S3 keyboard I/O code. I might update that a little bit, but in any case, this is where it is. And it will not have some of the changes I've made for some of the features that I'm looking at, because that is something that is extra and that is up to the individual. If you're using this code, it will behave like a standard keyboard, but you can add some features to it, as you can see when we do a code review. So this is where you can get the code from. Of course, all of these things will be links in the description, so including previous episodes and also some other information, the components that I used. So looking at this keyboard, there's a little bit of history here, which is kind of interesting. This particular keyboard was made by a company called Northgate Computer Systems, which is well and truly defunct by now. I don't know how long they lasted, but they were quite popular in the, like 1990 when I bought this keyboard. And the thing is that the original keyboards that came with the IBM PC was like this. And you might notice that, for instance, it had a control key here, and Alt was there, and caps lock was sort of relegated to somewhere over there. And in fact, that was a way better keyboard layout than what the later IBM AT and so on keyboards came out with, where they actually put the caps lock key where the control key was. And everyone was complaining about that because you kind of had muscle memory, using these keyboards. And some of the RS-232 terminals too, they would have the control key there. So it was a kind of a long-standing thing, but some people got used to. Although I've seen some IBM terminals that had a lock key there as well. And what the heck they used that caps lock for, it beats me, because it's a very useless key. And in fact, on my keyboards, I have a little a utility that I wrote many years ago, key mapper, that I can actually assign any key to something else, and I usually make the caps lock key just another shift key, because who needs it? But in any case, that's beside the point right now. Also notice that it has these function keys over here, 10 function keys on the left. And people got used to that, and a lot of old software, word processors and spreadsheets, I'm thinking Lotus 123 for instance, and so on, they came with little plastic guides that actually would fit over top of these keys, and it would have stuff printed on it, to the left, to say, okay, F1 is help, or maybe, or probably, and F2 does this, F3 does that, and so on, to remind you what these keys were for. And that is why, if you look at this keyboard that we have here, they actually decided to give everyone whatever they wanted. They put 10 function keys here, and those guides would still work with those. And they put the 12 function keys up the top here, and then they added the 2 extra ones there as well. F11 and F12, they were added later. And they put the control key back where it belonged, and caps lock is over here, and you'll find that there's a couple of keys here. Today you'll find a Windows key here, and another menu key over here, but they put the little tilde thing and so on, and an extra asterisk over here. In any case, and this particular keyboard had a lot of features over here. It has SF select. You could actually select what these keys do, whether they are just function keys. They defaulted to shift function, that's why it says F1, but you can hit that and you can change the mode of them to make normal function keys. Comma period lock for Europeans or non-English. They use a comma for where the decimal point is in numeric values. And you can even change the rate select when you hold the key down, how quickly the characters will repeat. You can go fast, slow, medium, and so on. There's also an extra key here, which at the time, I think there was a little driver you would load, and then you could use that, and I believe, if I remember correctly, I might stand corrected, but it had something to do, you could create macros for certain key combinations and stuff like that, like you see in some of the modern keyboards as well. Anyway, so that is that. Now I have already converted this keyboard. If you look at the later on at the controller board, you will notice, let me lift it up here. You will notice that this particular keyboard had 2 sockets. There was one here and there was one there. And those sockets were like 4-pin DIN sockets. I have no idea what they were for. I have never used them, even 34 years ago. So I removed those sockets from the controller board, which means that now I had 2 holes there that I could use that weren't blocked by them. And I put a switch here, and I put a USB 3 charge socket over here. And this switch over here is a center off. If I put it in the center, the keyboard is off, like so. If I put it to the right, it runs off this cell. If I put it to the left, it will run off the USB port. So I can actually plug in a USB cable over here, and you see it is not on right now, but when I plug it in, see, now it is on, and while it is actually on, it will also be charging this cell. And I can tell because in the distance there, my little charge station says it's now drawing 0.7 amps, and the keyboard doesn't draw that much. Keyboard tends to draw about 250 milliamps on average, and sometimes a little less, depending on what you're doing. Anyway, so that's the story on this keyboard, and as I said, this keyboard now is actually running internally, and we will open it up and have a look at it. I wired in a charge and boost board for that cell and to be able to charge it. And I put a little Chow ESP32 S3 board in there, which is picking up the USB signals from that little board out of that converter, and is then we can then interact with it and intercept the hit codes and do some work on it, as you'll see when we do the code review. And also that will allow us to then output it as a Bluetooth signal. And this particular keyboard right now is actually hooked up, and I can show that by going to show Bluetooth devices, going to display capture, and you will see that I've called it OmniKey, and it is over here, and it says it's connected. Now this keyboard, I have already converted it, and in here this is actually a little antenna that came with the Chow ESP32 S3 board. It'll plug in. I currently have it connected to an external antenna for testing, like a big one over here. But when I put it all back together again, I will be plugging in this little cable over here into that port over there. Inside I have, now this is my testing version, so what I've actually done is I have used some of that nano tape with the little microcontroller here, and I put little plugs and sockets in a lot of different places here, so I can, because when you're programming this thing, this is the D plus and D minus for the USB port. We'll be talking about that a little bit more, but you have to unplug that and plug the USB-C cable in there and hold down the little button that's next to it there, that's hot, that you won't be able to see. It's just tiny, and then it goes into device mode, and then you can program it. And then because there's only one USB port on this little board, some of the other boards I have that you've seen in other episodes, they've got two sockets, so you don't have to do that. But in any case, so I've got lots of plugs with sockets, power, and these ones here are connected D0, 1, 2, and 3. They actually go to these LEDs here, so we can control those. This is the switch. I've got the wiring going here. There's a little board in here. This is one of my favorite little boards. This thing can actually charge the lithium-ion cell, but it can also power something. There's a tiny trim pot in there. You can actually set the voltage to different voltages, but I got that trimmed in order to output 5 volts. And so then the 3.7 to 4 odd volts coming from the cell here gets turned into 5 volts. There's a boost circuit in here, and I put a couple of extra capacitors on there. These little boards here, they're not bad, but I just like to quieten them down, the noise. So I put 100 nanofarad and a 220 microfarad capacitor there. I put another little 100 nanofarad capacitor on here for the microcontroller to keep things nice and smooth. And so I got that connected. Underneath the keyboard, I have these wires connected to actually this PS2 socket here. So there's power. The red one is plus 5 volts, and the green one is ground, and the yellow and orange ones are the clock and the data. And I am feeding those into this little board here. This little board actually comes from an adapter that I have had for over 20 years or something. We used to have little sockets for a mouse and a keyboard, in fact, and a USB plug, USB 2 plug on the other end. And when I opened it up, that little board that you see was actually inside. Let's recap then. In some of the previous episodes, as I said, I was planning to hook it up to the PS2 signals directly, but with this little board over here, we no longer have to. So, as I said, what I've actually done is I soldered some wires. Now, on the bottom of this little board are two little pads, D plus and D minus. So I went to the internet and looked at some images. I couldn't remember which one was green and which one was white. I've seen them before in different places. Got some green and white wire, and I looked it up. And the first image I looked at on the internet was that white was D plus and green was D minus. So I thought, okay. So I soldered those wires accordingly, and on this little board here, which you won't be able to see, but it is actually printed on there, D plus and D minus. So I just connected those with those actual pads on there, and I then, as I said, wired in the data and the clock from the PS2. It's underneath the board. I soldered on some wires, put some hot glue on there to stop the wires from sort of ripping off. But what happened was that I wired all this up and double checked it, and I plugged it in and got it running, and nothing happened. And so then I started to backtrack, and I disconnected this thing here and picked up the clock and the data signals on the oscilloscope, and I noticed that the clock and data signals were being held low, and normally they are high when it is inactive. And if I hit enough keys over here and did some fiddling and so on, occasionally I saw a little blip there where it would high, then it would show a little bit of data there, and then it would go low again. And I started to have a look. I thought, well, what could possibly be the cause of that? As soon as I plugged this board back in, it pulled it low, and if I unplugged it, it was high, and I could hit keys on the keyboard, and they showed the correct data. So obviously the keyboard was working, and it wasn't the PS2 signals. So I knew that then, and I thought, well, there is something going on. Either this board has gone bad, or there's something going on with the USB signals. So I looked at the internet again, and then I noticed there were other images that said the opposite, that actually D plus and D minus were, the opposite way around. Green D plus and white being D minus. And I don't know exactly what that was all about. I've never taken much notice of these signals, and I thought you would always connect D minus, D minus, D plus, and D plus. But I thought, you know what? There's a hunch. I've been in this game long enough. Sometimes you have to cross over cables and stuff. So I actually crossed over those wires where previously was D minus. I made it D plus, and D plus and D minus, and lo and behold, it started working. And what happened is that as soon as it was actually making a proper USB connection, it actually pulled the signals high and allowed the data to come through, and it was outputting the data to this USB port here. So obviously there's an untold thing that I hadn't seen before, that if you're not connected to USB, you simply pull the data and clock signals low, and that, I guess, signals to the keyboard that there is nothing connected, so don't output any data or something like that. It's kind of interesting. And so at that stage it started working, and I have also actually, if we look at this over here, finally you'll find that I found that those pins over here, those three pins are connected to those three LEDs. This is VCC. There's actually no ground on this connector, interestingly, and when these signals are pulled low, the LEDs come on, and because after all it's got VCC and a resistor to the LED, so you pull them low and then they will glow. So I disconnect. I removed those little jumpers that were there, and I soldered these 3 wires in place. And these 3 wires are actually going to a little socket over here, which is connected to D0, D1, and D2. So we actually have to control these LEDs from our microcontroller, because what happens is with the HID protocol, and whether you are at USB or you are in Bluetooth, when you hit things like numlock or scroll lock or caps lock, for instance, that key code is sent out to like the PC. The PC then says, oh, okay, we're in numlock mode, but then it sends a message back saying, okay, turn on the numlock LED. And this is something that we are responsible for now. So therefore, we have to be able to control these LEDs. So that's all the wiring that was required. And the actual circuit, let me zoom in on that a bit so you can see it better. Alright, so this here is the circuit that we have, how we got it connected. At the center of it actually is a switch here, a single pole double throw center off position switch. So you can see from that, this is a charge boost board. It has the battery permanently connected to it, and this little board here has got like 2 LEDs on it, the green and the red. Green says it's fully charged and red is while it is charging. So as soon as you plug in the USB cable over here to provide power, goes to the V in on that board, and it will actually attempt to charge the battery if it is needed. As long as the battery is connected and charged, there will be a V out represented from the board, which is going to be plus 5 volts. Of course, it will also draw the power from the USB bus if needed. In any case, we've got the plus 5 volts output. We've got a couple of capacitors there to remove any remaining noise that the board might output, because it is, after all, a switch mode boost converter, so there's always a little noise, and I find it a good thing to put some little capacitors on the output of it to limit that. So therefore, when the switch is off, neither one of those poles is connected, so there is no VCC, which is of course going to these different places here, which means that if it is off and you've got the USB-C cable plugged in, it will still be able to charge. It's got V in and it'll charge the battery, so that's simply charging only. If the switch is set to this position here, it will actually take the D-bus plus 5 volts and it will connect it to the VCC, which then is actually, so then actually the USB-C charger is actually powering the microcontroller as well as that little converter board, and the keyboard is being presented there, so it's running everything, and the V out from the charge board is being ignored. If it is on the on position, the V out is actually presented as VCC, so now the actual battery voltage is being boosted to 5 volts, and it is presented to the ESP32 board as well as the converter as well as the keyboard. So in that case, the lithium ion cell is actually running everything. Now the output of the ESP32, as I have already said, there's got D0, D1 and D2 going to outputs, which actually when they go low, they will actually turn the caps lock, num lock and scroll lock LEDs on the keyboard. The clock and data inputs from the keyboard are coming into this converter board, and it is actually presenting the output as USB. So D plus on that little board is going to D minus on the pad on the ESP32, and D minus is going to D plus on the pad on the ESP32. It's got two little solder pads on the bottom for that purpose. And that's really all to say about it. It's actually a fairly simple circuit. So now let's have a look at the software, which is actually the more interesting part. Okay, so let's do a quick code review here. This code has already been reviewed in episode 7, so we won't go through the whole thing again. You can watch episode 7. There will be a link in the description of how to get to that episode. The code, of course, for that episode, which really hasn't changed, is on the GitHub site. Again, there's a link for that in the description as well. And there have been no changes that I've made to these files over here: BLE, hit KB, ESP, USB, host, EX. They are used as is. But I did add some code to the actual main CPP file, which is what we're looking at right now. And if any of you are really wanting that bit of code here that I've got in here, just let me know in the comments, and I will publish it on the internet somewhere for you guys to download. If you really want it, just let me know in the comments. So what I've actually done is, for testing, I have actually used the scroll lock key as a switch to go to different modes, on account that the scroll lock key has no possible use in modern software that I know of, not in Windows. Likewise, the pause key is a key that is of no use to anyone as far as I know, so I have also used that. The pause key actually puts it in a special mode whereby it will actually just display the internal variables, like this KB mode and insert mode, and the actual, when you hit a key, the actual hid key code will be displayed, and the modified keys, Control Alt Shift and so on, so that you can actually see what each key produces and what kind of messages are actually being sent and recorded. So that could be commented out actually for a working version, but it is good for debugging, and it is still there. So if you just hit scroll lock by itself, we pick that up and we make sure that the keyboard is in standard mode, which is a default. In that mode, it doesn't do anything. It just behaves like a stock standard keyboard. Every key would behave exactly the same as any other keyboard that you would expect. If you hit scroll lock plus control, it goes to this insert mode over here, and then you can actually hit the insert key to switch it from insert to overtype mode. And if you hit scroll lock plus alt, it actually goes to this mangle mode, and it actually uses this string over here, and it will translate the lowercase characters as is shown here by this string into this mangled stuff here. So A becomes at, and B becomes 6, and C becomes like a little left brace, ellipse, or whatever you call it. And the purpose of that we'll discuss in a minute. And here's a little bit of code that I entered. I've actually went through I mentioned last time in the previous episode I did something similar with insert mode, but I only had a few of these codes there, and I said, this was only just for testing. And I've actually gone through and checked all the codes, and this now is totally correct. If we receive any of those hid codes, these are actually text codes like A to Z, 1 to 9, and also, like backslash and question mark and less than and greater than, comma and dot, full stop and braces and brackets and what have you. All of those characters, of course, can be overtyped with, and therefore we need to know if it is a textual character, and that is what this little function here returns, it returns true. If it is a text character, that can overtype something. Obviously, control characters like enter and numlock and various F1, F2 function keys, they are not keys that should be used for overtyping because they have their own functions. Little function here to flash the LED, so we know that when we change modes, I'm flashing the scroll lock key like a few times, and so we can see that it took effect. And here we have the function that is used to actually change the keyboard mode. We are passing in the modifier, so we can check whether it is Control, Alt, or Shift. So we actually are resetting the LEDs. Then we update the LEDs to make sure that they are lit up correctly. Then if there are no modifiers that we are interested in, which is actually only 2 of them at this point, you would use 07 if shift is to be included in the future. Remember, I said there is a 4th mode that we're not using right now. If they are all 0, in other words, scroll lock was hit, but without any modifiers that we are interested in, we put it in standard mode. If, however, the control key was down, we will put it in insert mode, and we flash the LED 3 times, and we make sure that the finished state is that the LED should be left in. High is the default, but we are actually telling it that we want it, after it's flashing, it should be left in a low state. Similarly, if we get a alt bit set on the modifier, then we put it in mangle mode, and now we are flashing the LED 3 times as well, but we actually turn on all the LEDs, low of course, meaning that the LED is on, remember, it is active low. And if we receive anything else, if it gets for some reason, then we just leave it in KB standard mode. There is a function here to convert an ASCII code, like for instance, the ASCII code for an uppercase A is 41 hex, a space is 20 hex, a lowercase a is 61 hex. So we pass that in as the actual character, and it returns a hit keyboard report, because that is the most likely thing that you want this code to go into, because we need to return a key code and a modifier, because after all, like for instance, if you were passing in an uppercase A, then you would have to have the key code for that, and the modifier would say shift, because it's a shifted A, right? And so that's what that does. It actually converts the ASCII code to a key code. Now, in order to do that, we use this table over here. And if you look at that, where that comes from, that is actually in this file here. And here's ASCII to key code. Gives you an example of how to use it, and that's exactly what we have done. And as you can see, as I said, I was talking about the uppercase A. So if we look at the 41 hex, the uppercase A, we see that it is hit code 4, and we have the other dimension there says 1. That's actually whether it's shifted or not, so it's a shifted key, so it's uppercase. If we now look at the lowercase, which is over here, 61 hex, we see that it's got the same code, but now there is no shift, it's 0. So you can see that happening here. the first dimension 0 is actually the modifier, and the actual key code is actually the second dimension. Okay, then as before, we are actually responding to the on-keyboard callback. There's a number of callbacks there. There's callbacks that return the ASCII code and so on and so on. But we don't need those. In this instance, we want to get the hit code, and we want it as a report with the modifier and the key code in it. So we have the report here, the current report, the key that was hit. We have the previous report, that was the last key that was hit. Sometimes you want to know that in case you want to have a special, where you want to respond to a couple of two keys in succession or something, and you can find that out there. And this is actually a special a decoded modifier. It actually contains I think it's booleans for shift and for win and control and alt and all that kind of stuff, but we're not actually using that here. We're using the actual hexadecimal modifier instead. Okay, so if the key code is actually the pause key, then we put it in pause mode, and again we will see later on what that does when we actually test it. If we hit scroll lock, then we actually call that function we looked at earlier, change KB mode to whatever the value that modifier is, will determine whether we are in insert mangle mode or whatever. And if in fact the keyboard mode currently is insert, if it is in insert mode, then it is checking if while it is in that mode you actually hit the insert key. Then it'll toggle the insert mode from overtype to insert mode, and you'll notice that a couple of these things have report no key pressed, because in that case we don't pass on the insert key to actually the Windows operating system or whatever computer you got this plugged into. We just say, okay, we've used the key, so we're not actually passing it on, and that's what's being done there. If, however, while it is in insert mode, we hit any other key, then we're actually checking if it is in insert mode. If insert mode is active, then we want to know if the actual character that is being reported is actually a textual character, as I explained earlier. If it is, then it actually creates a temporary report with a delete key. So therefore, wherever the cursor is, it is going to actually delete the character under the cursor. And then we actually send the actual real report, which is done over here actually. So that actually simulates overtype mode. Now, if the keyboard mode is in mangle mode, we actually change the key code to ASCII, because we want to know what key it is. Therefore, after it's been modified to ASCII, we can say, okay, is it a letter from lowercase a to lowercase z, or z if you're American? And then we are actually subtracting lowercase a code from it. So we end up, if it is a lowercase a, we actually end up with a 0. Therefore, we know the offset into the string, which remember is over here. So offset 0 would be, for the lowercase a, and it's going to actually become an @ sign. And so that's what we're doing here. We're actually changing the character to the mangled character. And then we actually turn it back to a key code for the report. and that is what we looked at earlier. That's the function that actually uses that array to actually turn it from ASCII to a key code. Now, if it happens to be in pause mode, then it is actually going to give us some debug information. What the current keyboard mode is, if it actually is in insert mode or not, the actual hexadecimal value of the key code, and the modifier. So that, as I said, that is for you can hit any keys, and you'll see that happening when we test it. And that's really all there is to it. Of course, you know, we got these three LEDs, caps lock, num lock, and scroll lock. So we are controlling those with the ESP32 board. So we got the pin modes have to be defined as output for those three, and the rest is the same. We reset the keyboard LEDs to the current mode, and that's it. That's all there is to it, to the software. So now let's have a look if it works. Alright, so let's try it out. The first thing we see over here is pause mode, so we might as well try that out first. Put the cursor in Notepad over here, and I'm going to turn caps lock off because that's still on, and I'm going to hit pause, and you'll see we get debug information. So that's actually the pause key, 48 hex. If I hit another key like A, you'll get two reports each. You see keyboard mode is 0, insert mode 0, key code is 40 hex, so that's A, and there's no modifier. If I now hit like Control A, so there's the control key and A, and then so the key code is actually 0, but the modifier is 1. See, that's for control. And then we hit A, so the key code is 4, and the modifier is still 1. Key code is 0, so I release the A in other words, but the modifier, the control key is still down, and then finally there's a little report there that says, okay, everything is up. No more modifier, no more key. So that's kind of how the keyboard reports stuff. Of course, if I go like this, you can see it on a single line. That one might be more clear. Okay, so that's pause mode. So hit pause again, turns pause mode off. And let's make that window a little bit smaller again. Alright, so then there is, if scroll lock is pressed, then it actually goes to this change keyboard mode function here. So it is actually checking if there are any modifiers. If there's no modifiers, then it'll actually put the keyboard back in standard mode, which is actually what we're in right now. If there is a modifier, a control bit set, then it goes to insert mode. So let's try that. We hit Control scroll lock, and you'll see that flashing there 3 times. That is what I've coded in there. See, flashes 3 times. And now let's go back into Notepad. We'll do a Control A and a delete to get rid of this stuff. And if I press a string like this, and I put the cursor in the middle there, and I hit some other keys, it'll just insert them. Now if I hit the insert key, now it should be overtyping. There we go. Insert overtype mode. So that's working. And so now I'm going to hit scroll lock again, and now we're in standard mode. So we're also always, insert doesn't do anything now because we're in standard mode. So that's that. So that's working. Then the next thing that we have is if the alt bit is set, we go into this mangle mode. Now we're going to be, you remember in the old days people used to, you can't remember passwords, and it's still a problem. Of course, you got software nowadays you could subscribe to or use, like LastPass and Bitwarden and so on, but it's still a pain in the neck. So if I type like this password or something else, whatever. So now I'm going to hit Control, Alt scroll walk rather, and you see that was flashing and all three lights are now on, so we know that we are in that mode. And so now if I hit type password, I actually get sort of a string there with that's what it's supposed to come up with. And so that says password dirty dog. So of course that string that I have up the top here is what is used, this string over here. You can put anything in there. If you change that to something else, it could be. So as you can see, A is going to be an at, and a B is going to be a 6 and a bracket. So if I go over here and hit A, B, C, you'll see that that is what is coming out. And if I hit uppercase, it's not actually converting them. So you could actually say pa uppercase W and uppercase P. So if you've got an account with like some Bank of America or something, you could type BANK with some capitals mixed in. So that could be your password for Bank of America. This is what I typed. And so that is easy to remember, right? So you can make up passwords like this for all of your accounts and keep track of them just by remembering what you typed. You don't have to remember, B at dash ampersand 0 or O rather, and so on. If you type it all in lowercase, it would look like that. So I thought that's kind of a cool thing to have in your keyboard. You can mangle sort of words that you can remember and use them as passwords. Anyway, so all that is working, and we have converted this keyboard into a wireless Bluetooth keyboard. And if I plug in now a USB cable, anyway, let's change cameras here. Okay, so all the lights are on, so we're still in that mangle mode. So it's scroll lock, now it's off. And so, but now we're actually running, nothing is plugged in, so we're running off that that one lithium ion cell over there. But if I now plug in the USB cable, I haven't screwed down the top cover yet, like that. It's drawing 0.6 of an amp, but that is because it is actually charging the battery as well as the running keyboard now off external power. And I can actually switch this off, and now it is drawing 0.1 amps, so the battery is nearly full. So that's That's the only current that it is drawing, and it is actually charging the battery. Okay, that's all we've got, and don't forget to subscribe and like and all that kind of stuff, because that would be most helpful. And we're going to be doing some other projects soon. There'll be some episodes on that. I have a few devices that I've bought, including this Lego T-Deck thing and so on, so we're going to be looking at that. Anyway, I'll see you guys later. Bye-bye.